So welcome back. Second part of the morning. Three interesting She is in chess distribution, and she works in the strategy department, and she is involved mainly with Grid4U activities. Since 2004, she has worked on FP6, FP7 projects, and sorry, I have to say it, I loved it. She's graduated at the Faculty of Agrobiology, Food and Natural Resources in Chess University. So. Life Science 2005, so I had to say it, sorry. And she will be joined on stage also by Rémi Garot. He's in ERDF. We also already had a presentation by ERDF this morning. You know very well the company. And he's the coordinator for the Grid4U activities. Thank you, stage is yours.
Good morning still, ladies and gentlemen. Just after the introduction, I would like to say that I'm really a technically oriented person, as you've noticed, so you can ask really technical questions at the end of the presentation, which is going to be about Smart Region, which is a pilot project on smart grids of Chess Group. Okay, this is the outline of my presentation. I'm going to talk about Smart Region and why we do it in the Chess Group. So as it's part of so-called future motion concept, I'm going to tell you a few words about this, and then I'm going to focus on Smart Region as such. So I'll outline the location, partners, time schedule, and goals and activities of the project. I'll also ask the coordinator of the Grid4U project to say a few words about the Grid4U project, which a Smart Region is part of. And at the end, I'll focus a little bit more on the individual goals or objectives of the Smart Region project. So let's start with the first part. Smart Region is actually a part of it's a research and development activity of the Chess Group, which is called Future Motion. And that is activity which is focused on development and research in the field of energy. It's not just focused on the distribution, it's also focused on the energy production and energy consumption. So the activities are focused to actually bring new and modern and efficient approaches to the energy activities of the chess distribution. There are four main areas involved in the Future Motion. So this is a R&D cooperation of a Chess Group with the different R&D institutions and universities in the Czech Republic. Then there is a part which is focused on local energy production. So that means the distributed energy resources and renewables. One part also focuses strongly on the electromobility, so electric vehicles and the infrastructure. And the last but not least focuses on the active demand, and there we've got the smart grid and smart metering projects. The Smart Region actually covers all four mentioned activities together, and it focuses on the improvement of the grid. It tries to make the grid more reliable by putting new and smart technologies into the distribution grid. If you'd like to learn some more information, you can check the website, which is just on the bottom of this slide. I'll now tell you a little bit about Smart Region itself. Smart Region is carried out in the Czech Republic, in the northeast part of the Czech Republic, in a town called Vrchlabí, which is just below the highest Czech mountains. We cooperate on the project with a other partners outside of the CHESS group, namely Cisco, ABB, Siemens, and Current. And the project is carried out within years 2011 to 2016. What are the overall goals and expectations of the smart region? I just put it really simple because these are the most important messages that I would like you to remember about the smart region. We actually focus on 3 different areas, 3 different automations. First is the mid-voltage automation of the grid, then there is low-voltage automation of the grid, and last but not least, there is an automated island operation in the area of Vrchlabí. So while we do it, we want to have better control of our grid on different levels and in different activities. So we try to do our best to have faster localization and isolation of failures. We try to improve our site safety indicators, reduce the voltage violation, decrease energy losses, and increase dependability of the grid. Here you can see the schedule. We have actually divided our activities within the project into, let's say, four types. Firstly, we focused on the planning of the whole demonstration project. This phase is now closed. We already know how and what we want to do it and when. Next, we also started the research and development activities, including the laboratory test, where we test the different equipment and the communication of the equipment, automation equipment in the grid. Then the next phase, it's about the implementation, which means that the tested solution is actually implemented into the real grid, and at the end of the project, we'll evaluate the proposed setup or architecture of the grid, whether it works or not. We're going to evaluate the KPIs, which we set at the beginning of the project, and we'll try to help the European DSO to use or not to use the solution that we actually tested. I would just now like to invite Remy as a coordinator of the Grid for You project, to tell you a bit about the Grid for You project as such and the place of smart region in there.
Thank you. Vrchlabí Smart Region is part of the Grid for You project. And Grid for You is the biggest European project about smart grid. This project is managed by 6 leader DSOs, Enel, Iberdrola, CHESS, Vattenfall, RWE, and ERDF. The project is coordinated by ERDF. In this project, we would like to setting up a large-scale demonstration of distribution network able to integrate distributed generation and able to develop customer participation. We will spend 54 million euros, so it's very, very big project, and as a whole, we are gathering nearly 30 partners, such as equipment manufacturer, DSOs, of course, and university. So there is 6 demos in 6 countries. 1 demo in Spain, 1 in Italy, 1 in Czech Republic, 1 in Germany, 1 in Sweden, and 1 in France. Each demo is managed by a distributor, a DSO, and each demo has a specific boundaries condition in order to prevent and avoid effort overlapping. So here we are not talking about standalone demos, we are talking about complementary demos. It means that we will test all scenarios once, share the information to all actors, and thus prevent effort overlapping. So for example, for each demo there is specific climate condition. If you want more information about the other demo, you could visit the Grid for You website, and we are also organizing a presentation during the day in the stand D 23. This is the Accenture one. And there was a video, a kind of video, and a presentation done by ERDF. Thank you.
Thank you very much as well. I didn't make it better. I think you left this here, Remy. Okay. So now I move to a bit more technical part of my presentation, and I will tell you more about the objectives of a smart region project. First of all, I'll focus on the mid-voltage automation, which is one of the 3 objectives. And as you can see on the slide, we're working on the mid-voltage automation together with our partners, ABB, Siemens and Cisco. And we try to prove that the new grid setup together with what we call disconnection, secondary substation, and SCADA and the local SCADA can actually make the grid more reliable, and that the equipment can provide faster failure localization and isolation. So how does it look like? We're doing the mid-voltage automation in the whole town of Vrchlabí, which has approximately 5,000 of final consumers. So we address that. We've got 31 secondary substations there, and the grid topology looks like this. With in the green color, you may see there the disconnection points. Or the disconnection substation, as we call. These are there because we need to disconnect the smallest possible part of the grid affected by the failure on the mid voltage. I'll show you on my next slide how it actually works. So if the failure appears in the grid, for example, as where you see that it just appeared. I don't know if you can see the pointer. If the failure is here, then the current status, so the present situation would be that whole part, this part of the grid, would be without the electricity supply. And that's just not a very good situation because it's too many consumers actually affected by the failure. So what we'll try to do in the project, we'll try to minimize the impact of the failure by switching the switches, or disconnecting the switches in the disconnection substation. So we actually isolate the failure. And after that, we use local or regional SCADA, as we call it, and the superior SCADA to actually minimize the failure just between the 2 substations, which are the closest to the failure. For that, we're using the indicator of short circuit currents. The second objective of our project is the low voltage automation. Here we try to prove that the new architecture will actually improve the reliability of the grid, will reduce the impact of potential failures on the low voltage grid, and minimize the number of affected consumers. Nowadays, we've got just the linear grid topology, but now in the project, we're going to test, as you can see here on this picture, we're going to test to have a topology with interconnected 2 substations. One you can see on the left, what's the pointer? On the left top part, and the other one on the bottom. And they are actually interconnected in the low voltage substation, which is marked by 3, but I don't know if you can see it okay, but it's just where the green and red lines meet. So we're using remotely or controlled devices in the low voltage substation to reduce the failures. So we can see that if the failure occurs, for example, in the area between the low voltage substation 1 and 2, then the whole part, which was previously fed by the red part, is without the electricity supply, so now it's black. What is done here in the situation is that the left circuit breaker in the first low voltage substation is disconnected, as well as the circuit breaker in the third, in the substation number 3. And what our approach is is that we use the local SCADA to propose a new grid architecture, a new grid interconnection, and setting up new parameters on the circuit breakers so that we can minimize the impact of the failure. And what we do next is that we switch off the circuit breaker which is closest to the failure, which means the circuit breaker on the street, on the substation number 2. What happens next is we switch on again the circuit breaker in the first substation, which causes the bay, which is connected to the first substation that is now again supplied by the electricity. And the next step is to switch on again the circuit breaker in the street and the low voltage substation number 3, and then the grid is again connected to the grid via the substation, which is the secondary substation, which is at the bottom. So now we've localized and isolated the failure in the most efficient way as we can by only doing the automation steps. Last but not least, the third objective is about island operation. As what we try to do here is to propose a control of all phases of the island operation, which means we want to have automatically disconnection of the grid, of the part of the grid which is meant for the island operation. Then we want to have automated balance operation of the island, and then automated reconnection to the grid. While we're actually doing this exercise, we're doing this because we want to have proven solution for the grid once there is much more of distributed energy resources connected to the grid in the Czech Republic. As you can see, we're going to test this solution just on the part of the grid in Vrchlabí. There's going to be 7 substations within the tested area, and nearly 2,000 end consumers involved within this exercise. This is the grid topology for the island. We can use the grid topology of the mid-voltage network. For the island at the moment is shown at the green dashed line. That's the part we're going to test at the moment. What we're thinking about is to test the pink dash line area as well, because the CHP unit that is going to provide electricity to the grid is big enough to supply the electricity even to the other parts. But as at the bottom part, at the pink part, there is also included a hospital. We really first need to prove that the island operation is safe and reliable, and it will provide the services good enough even to serve for a hospital. How it works? In the case the failure is detected by the automation equipment called balance automation, or if the operator of superior SCADA decides to switch the area to the island operation, and the balance automation sends the commands to the disconnection points, so to the 2 green substations, to disconnect the island operation area from the rest of the grid. And the balance automation actually ensures that the power production and the power consumption at the moment of island operation is balanced. Once the failure is maintained, or once the operator of the superior SCADA decides that it is time to switch back to the standard conditions, then the balance automatics and the equipment called Syncrotact, which is responsible for synchronization of the phase, voltage and frequency of the CHP, actually provides the synchronization, and the grid, the island operation area can be connected back to the grid. So this is all my presentation. I'd like to thank you for the attention. I hope I made the time.
Thank you very much. It's perfect.